Hello, hello. All right. Hello, everybody. My name is Alvarius, and yeah, today I'm going to talk about MUD, which is an application framework for on-chain applications. Meaning it's a set of smart contracts and libraries and corresponding client-side integrations, which the goal of the whole thing is to make application development easier for on-chain development. And today I want to talk about 4 hacks that we implemented to make the developer experience easier for our users. And to give you some more context for where we're coming from is this. Our background is basically building fully on-chain games. So 3 years ago we started building a fully on-chain game, and we quickly had to realize that the developer experience of building fully on-chain games using Solidity on the EVM kind of sucked. On-chain games have a lot of state on-chain, and also all the logic is on-chain. And so the approach that we went with initially is basically what you see here. We defined a couple of structs for all the types of things that are in the game, and then we need to store those structs in storage on-chain. And so we create a mapping which goes from the ID of whatever we want to store, and then also to the struct of whatever we want to store. And then we also store an array of the IDs of all the things that are, so that we can iterate over that and return it to the client. And then we usually have a getter function which returns the initial state so that the client can load the initial state. And then we have an event that is emitted every time on-chain, every time anything changes, so that the client can update the state. The whole point of this is you have all your state and all your logic on-chain, but if you have an on-chain game, you also have a client that should display all the state of your game, and it should update every time anything happens in the game. And so this looks simple enough, and so this is the approach we took initially. But then once you get sufficiently complex, there's a lot of things in the game, and a lot of ways those things can change. And so it gets really complex really quickly. What you see here is a subset of the events of Dark Forest, which is one of the first on-chain games that heavily inspired MUD. What you don't see here is all of the things that also was in Dark Forest behind those events. So for each of these events is some entity in the world changed in some way, and so corresponding to this, there's also a bunch of client-side reducers for these events so that the state can be updated. There's the corresponding structs on the in your contracts. There's the corresponding mappings. There's the arrays. There's the getter functions, and there's the setter functions which manually emit an event whenever anything of these changes. And so as you develop your game, when you want to change the mechanics of your game, you basically have to drill down that change through your entire networking stack, and you have to change your structs, you have to change your getters, you have to change your setters, your events, and then the event reducers, and also that on the indexer. And yeah, so that kind of drove us crazy, and so we thought of ways to improve that and do that differently. And so what I want to do here basically today is walk you through that process that we went through and the result we ended up with. And again, there's a couple of hacks that we had to do, hacks in the positive sense here. We had to basically try to, get the functionality we wanted with maybe some features that were missing in the language that maybe will be added soon. But yeah, let me get started with what would be our dream developer experience as somebody who builds an on-chain app and want to synchronize the state to the client. Ideally, we would want to just set the state on-chain, and then automatically, magically, the entire state would be synchronized to our client, and we can just get the state on the client without having to write custom events, without having to write custom reducers, none of that. And so ideally, we would want to have some kind of data structure on-chain that enables that. And so that was basically our initial problem set when we got started implementing MUD. So essentially, how we got started is we have a contract. And before, we were emitting a specific event for every type of entity or for every thing in the game that changed. If we want to build one network synchronization stack, then we don't want to integrate every new event in that network synchronization stack. So ideally what we would want to have is an event that is the same event essentially for every state update. So essentially something that we would need is basically an event that includes the key of the thing that gets updated and the new value of the thing that gets updated. But the problem is the values have different types. It's not the same type, and you can't have an event with different types in your signature. So the way we got around this is by basically removing the types. So instead of having the actual value type in our event, we just remove the types. We just say it's bytes, which is basically the common type for all of the more specific types that we're using. And so we have an event now that is bytes 32 key and bytes value, and the value basically can be anything, anything we want it to be. But then that moves it improves the thing a little bit, but it creates a new problem. Like, how do we get from our actual type to the bytes? And before that, also, we ideally don't even want to emit that event manually, but we want to have that data structure or a library or something that emits that event automatically when any state changes. So ideally, what we would like to have here is a library that let's just call it store library, that essentially has a generic type T, and again, it lets us set our key, and then the value is T, and then what it does internally is emit the event and store the stuff in storage, and then when we get the value back from storage, it gives us back our type T, and what it does internally is it loads it from storage and decodes it as T. Again, this is not possible yet, so what we again have to do, basically the same trick as before, we just remove the types, and instead we have a function set and a function get, and both of them again just act on bytes. So we have our bytes key and our bytes value, and then when we that emits the event automatically and it sets our storage, and then in our getter we load the stuff from storage and then we return it again. So essentially what we want here now is that at least we don't have to emit the event manually anymore, and it stores it in storage automatically, and yeah, for getting there's nothing really special here. But it removes the problem again one step further. We still haven't found a way how to get from our actual type to bytes. So we basically still need our encoding function here. It just moves it outside of the library and into the consumer of the library. So the next problem is, how do we encode our types and how do we get those bytes? And there's actually a very simple solution to that. We could just use abi.encode, and that is what we did use in the beginning, which turns essentially any type you want to pass into bytes, and then we can just use that here. So library.set, we give our key, which is still bytes 32, and then we put in any value we have, that could be our custom struct, and then it turns it to bytes. The problem here is that ABI encode adds a lot of padding, and so if we want to store that in storage, like we do here in our library, then that creates a lot of overhead in storage. And so it's a little suboptimal. We started with that, but we realized, okay, this is actually creating a lot of gas overhead because we can't really pack anything in storage anymore. And so we thought, okay, what can we do differently? ABI encode packed is a little bit better here, because for any static type, it basically packs it into one blob of bytes that is tightly packed, and so storing that in storage is almost the same thing as what the Solidity compiler would do. But the problem here is that it doesn't work for all types. It doesn't work for arrays, for example. And so essentially to get around that, we had to implement our own encoding function for arrays specifically. So for static types, ABI encode packed is good enough, but for arrays it doesn't work, so we have to find some other solution. We actually found a proposal for Solidity for something like ABI encode tightly packed with support for arrays, but since it wasn't there yet when we got started, we couldn't use that. And so we have our encode function that is supposed to encode arrays. So how do we go about implementing that? The tricky thing here is that while ABI encode and ABI encode packed, they essentially accept arguments of different types and then do something with it internally. If we want to write a function in Solidity that accepts different types, that's a little bit more involved and more hard. So what we do here is we first implement the function itself, again, using kind of a similar trick as before by just falling back to bytes. And one thing that we can use here is that all of the arrays, like all primitive type arrays in Solidity, are actually padded to 32 bytes. And so we can implement our function using bytes 32 array as the type, basically. And then the actual element in the array has a different size, and it's either left padded or right padded. And so we have two more arguments here for the element size and for the bits of padding. So using that, we can implement the logic for packing the data tightly for arrays, but we still can't call that function with arrays of different types. And so what we have to do here, our third hack, is essentially we just create an overload for every possible primitive array type, and then using that, we in the end actually have a function that we can call with any array, or any primitive array type at least. And then internally, what it does is it casts it to a bytes 32 bytes 32 array, and then passes it to our implementation of the encoding function. And with that, we have already solved the encoding part of everything, but we're still missing the decoding part. So we can now pass in essentially almost any type to our either ABI encode packed or our custom encoding function, at least any primitive type. But we still can't decode the bytes when it comes back out of storage. And so essentially what we would like to have here is something like ABI encode, which actually has a very unique power to it, which is you can pass in the types as a second argument, and then what you get back is what you passed in as a second argument. So this is basically like a generic return type, which is what we would need for our implementation. But unfortunately, we didn't find a way to really work around that in code, at runtime essentially. So what we're doing instead here is code generation. So what actually happens in Mud is people define their data structures in a config file, and then we generate a library, basically a type wrapper library for them, which includes the setter functions, which essentially just call the lower level store library and our lower level encode function. And then for getting the values, okay, it's not cut off here. For getting the values, what it does is it essentially gets the value back out of the storage and then uses a custom slice implementation basically to get the bytes back out of the bytes blob and then cast it to the type that we want. And so in the end, what you get with those code-generated libraries is essentially what we wanted to have in the start. So you get this type library that you can use to set a value and to get the value, all with your expected types. And internally, it emits an event that we can then pick up in basically a default implementation of our sync stack. And then what you get is you just set the value, like you just write your code as you would before, except you don't have to think of data synchronization at all anymore. And all the data is basically magically replicated to your client. So those are the 4 hacks we needed. For generic signatures, we cast everything to bytes. We implement something like ABI.encode tightly packed in Solidity. If we need an overload, or if we need a function that accepts every primitive type, what we can do is an overload for every possible primitive type. And then as a fallback, if nothing else helps, then we use CodeGen to get, for example, generic return types. If you have a simpler solution to this than what we came up with, I would love to talk. And I think after me, there's a talk about experimental Solidity features. So I'm very, very excited to hear that. Maybe it makes some of the stuff unnecessary. Thank you.